Okay, so what we're going to do is take a quick tour through the course. We're going to look at all the topics that we've seen in the course, and we're going to look at some focus topics for the final. And we'll be taking breaks, 5 or so minutes to have a go at some questions, either on your own or maybe in pairs. Given how many of you there are, it will probably be, we'll just take 5 minutes, have a go at a question, and then we'll come back together and we'll see the solution. So the focus will be very much on what's in the final and what you're going to see in terms of examples of questions. I do intend the final to be a lot easier than what you've seen in the chapter tests and the assignments. So in some sense, you've done the hard part at this point of the course. So you shouldn't be worried about the difficulty of the final compared to maybe what you've seen over the course of the class so far. So on the left, we've got some slides over here. And then on the right, I'll be doing some drawing as we go along. So hopefully everyone can see both of those screens there. Now, given that I have a lot of screens going on in front of me, if someone has a question or wants to interrupt me or point of clarification or anything like that, please just unmute yourself and talk at me because I won't have much chance to monitor the chat given I've got to keep eyes on a lot of things here. Okay, so that's the intro spiel. Let's have a look at the slides on the left. So what have we seen over the course of this class? We've seen a whole lot of material. So let's kind of break it down into some more manageable chunks. Now, what I've done here is come up with a little roadmap of kind of what this course has looked like. So bottom left, here we were 10 weeks ago at the very beginning. And what we've seen along the way are 5 points of interest. We've completed this class in 5 two-week blocks. So here are the little points of interest. And we've also encountered some obstacles, right, along the way. That's what these hills are supposed to be. And what we've ended up with right now, we're at the very end, we're at the top of this big mountain we've climbed over the last maybe 4 weeks or so. So what we're going to do is talk about what we've done along the way on this roadmap. So let's start. Way back at the start of the quarter, we did the first 2 weeks and we started looking at some stuff about deductive logic. We started looking in detail at what arguments are. And at the end of that 2 weeks, you took a test that assessed your understanding of all of that material. So what was in the material from those first 2 weeks? We looked at simple and complex statements. We looked at truth tables in some detail. We did a lot of those. We looked at simple and complex properties. And then we looked at the corresponding tables for properties. So we did a lot of presence tables. We then looked at testing arguments for validity using truth tables. We looked at arguments, like I said, in more detail. We looked at what logic is, and we looked at putting arguments into standard form. And we then encountered 2 types of probability. We encountered inductive probability and we encountered epistemic probability. So quite a bit was packed into those first 2 weeks. It was kind of a crash course in deductive logic. So what should you spend your time focusing on for the final? You should spend your time focusing on testing arguments for validity using truth tables and what we've learned about inductive probability. Now, of course, when you test arguments for validity using a truth table, we've kind of built in some of those other topics as well. So simple and complex statements, truth tables, that all feeds into testing an argument for validity using the truth table. But to help kind of manage all this information, what we said at the end or towards the end of those first 2 weeks was something like this. So we were interested in arguments. And what we did was classify kinds of arguments. And we asked, well, what makes this type of argument good? What makes this type of argument bad? So what we came up with was a good and bad classification of 2 types of arguments. We looked at deductive arguments and we looked at inductive arguments. And so this table we saw in the lecture videos. And so what makes a deductive argument good? That means you've got a valid argument. And what makes a deductive argument bad? Well, that would be if it was invalid. And so the point was these terms, valid and invalid, they apply to deductive arguments, not to inductive arguments. And so we asked, well, how would we describe good and bad inductive arguments? And the words we used for those, the strong inductive arguments are the good ones. Weak inductive arguments are the bad ones. And so this is the classification that we kind of laid out towards the end of those first 2 weeks about arguments, what they are, and how you would describe them. And so that's what this focus for the final slide is really getting at. There'll be one focus on deductive arguments where you're testing for validity, and there'll be another focus on inductive arguments where you're asked about the strength and weakness of some arguments. So this brings us to the first of our kind of example practice questions. So let me scroll down. So this is validity. So we're talking about deductive arguments first. And of course, you've seen this type of question before on the first chapter test. So here's another example of what you can expect to see on Monday. It says, using a truth table, show the following argument is invalid. Move that down. The argument reads P v Q. Q, so there are your 2 premises, and the conclusion of the argument is P. And then you are directed to say exactly what it is about your truth table that shows this argument to be invalid. So what we're going to do is pause for around 5 minutes or so. I want everyone to have a go at this question on their own. And then after 5 minutes has passed, we'll come back together and I will go through the solution on the screen. So we'll come back together at about 9:15. I'm going to try and pause the recording. Okay, it's 9:15, so we're going to come back together and I'll walk through the answer to this question. So you've got to use what you know about truth tables, and we've got to test this argument for validity. So step 1, you're going to have to actually construct the truth table. You'll get some points for that sort of thing. And then you've got to focus on the directive that's extra at the bottom. So you've got to say what it is about your truth table that shows this argument to be invalid. So let's go ahead and construct this truth table. So the way I usually do these things is I'll include all of the intermediate steps. When things are more complicated than this argument here, you won't lose marks as long as your truth table is correct for missing out intermediate steps and building up to those complex formula that you might see, those complex statements. But it's a good idea to do that to keep track of things. And I know I've said this type of thing before. So we start with P and Q. We start the same way. P will be true, true, false, false. Q will be true, false, true, false. And now we can notice a few things. P and Q both appear in this argument. P is the conclusion. Q is one of the premises. So all we've got to do a very easy third step is construct the truth table for the first premise of the argument, so PVQ. So that's what we're going to have in the table here. And that's an easy one. It's a one step for us. So we just use the rules for truth tables about disjunctions. We know that that truth table, P is true and Q is true, then PVQ is true. P is true, Q is false, PVQ is true. P is false and Q is true, PVQ is true. And when they're both false, the disjunction is false. So what we've got here is everything we need. We've got one of the premises here. We've got the other premise here. And we've got the conclusion, which happens to be Q. So here is the conclusion. So we've constructed the truth table. So that was job one. And all we've got to check is whether this argument is valid using this truth table. And how do we do that? Well, we know that an argument is valid just in case there are no rows of our truth table in which all of the premises are true and the conclusion is false. So we've got to check row by row of this truth table whether all of our premises are true and the conclusion is false. So if we look at row one here, and we're kind of working from right to left because the premises are on the right, the conclusion is on the left, we can see that both of our premises are true, but the conclusion is true as well. So this row is a valid instance because it's not the case that all of the premises are true and the conclusion is false. The conclusion is true in this row. What about this row? Are all of the premises true? Well, in this row, they are not both true because Q, one of the premises, is false. And so this row is a valid instance because it's not the case that all of the premises are true. So it can't be the case that all of the premises are true and the conclusion is false. What about this row? So the third one. Here, both of the premises are true. And if we look over on the left-hand side, we see that the conclusion is false here. So this is an instance in which both of our premises are true and the conclusion is false. So this row is an invalid instance. And of course, really, that's all the work you would have to do because you have now shown that it's invalid. If there is at least one invalid instance, then your argument's invalid. For completion, let's just have a look at the bottom row. Is it the case there that all of the premises are true and the conclusion false? No, it's not. In the bottom row, both of the premises are false. So it's not the case that both premises are true. So it can't be the case that both premises are true and the conclusion is false. So this row is a valid instance, but we've got one invalid instance in there. It's this row that's throwing everything off. And so if you wrote, like I have at the side, and indicate which of these rows are an invalid instance, that takes care of this second directive. So you've got to say what it is about your truth table that shows it to be invalid. So you do something like this, or say something like, there is at least one row in which all of the premises are true and the conclusion is false. Just checking the chat. Thank you, Fabiola. And like Fabiola just said in the chat, validity, there are no cases in which all of your premises are true and your conclusion is false. So that's how we take care of this type of question. Now, looking back at the left-hand side of my screen again, so we've taken care of validity here. So we're going to have a look at an example question that tests your understanding of inductive probability. Let me scroll down. So here we are, inductive logic, inductive probability, that should say. So here is an example question. I'm sure you all remember this type of question from the first test. These were difficult. Now, there's a few reasons why a question on a test might be difficult. Either it's conceptually difficult, maybe translating the question that I'm asking you into the right kind of math, for example, like we've seen towards the end of this class. That can make a question difficult. There's also a sense in which a question is difficult because not many people got it right on the test. Now, there are a few questions on the final that are of both of those types of difficulty I've just described. So where it wasn't done so well on a previous chapter test, I may have included something similar on the final. But whereas we had like 5 of these questions on the chapter test, you'll only get 1 or 2 on the final. So it's good to be able to practice these because, you know, we want to see some improvement since those first 2 weeks of the course. So here is the example question, testing inductive probability. It says, consider the argument below. Which of the following, if true, most weakens this argument? And you don't need to justify your answer. What that means is you should not leave this blank, even if you don't know. So what does the argument say? It says, premise 1, the mayor has been accused of taking a bribe based on the fact that a consultant that does business with the city paid for improvements to the mayor's vacation home. Premise 2, the mayor said he paid for every bill for those improvements that were presented to him. And the conclusion, therefore, those who accused the mayor of taking bribes were wrong. So you're asked which of the following principles, if true, most weakens this argument. So number 1, authorities are investigating the consultant for taking bribes from officials of other cities. 2, the mayor was aware that many of the bills were being presented to the consultant rather than to the mayor. 3, the building contractor in charge of the improvements to the mayor's house had done business with the city in the past. And 4, the amount of money that the city paid the consultant over the last year greatly exceeded the cost of the improvements to the mayor's house. So what I want you to do is we're going to take 2 or 3 minutes. I originally was going to put you in pairs, but I think given time constraints and the amount of screens I have going on and the fact that you have to do the final on your own, I think we'll just have a go at these questions individually, then we'll come back together and go through the answer. So take 2 or 3 minutes, have a think about which one of these most weakens the argument. I will then go through them and give you some tips on what you should be doing with questions like these. Okay, we're recording again. So let's go through which one of these most weakens this argument. Now, you know, my tips for these kind of question is when you get in your practicing, so look back at those second assignments that we did, look back at the extra set of problems I put up about necessary and sufficient questions. They will get you used to reading this type of complex question. It's just as important to know why answers are wrong as it is to know why the one that's correct is in fact correct for these questions. If you know why some are wrong, you can eliminate them, and that's helpful for these types of questions. So let's look at answer number 1. It says, authorities are investigating the consultant for taking bribes from officials of other cities. Now, does this weaken the argument? Well, if we think about it, answer number 1 doesn't really say anything about what the mayor is doing. You know, if someone that you do business with takes bribes, it wouldn't be fair for me to implicate you as well, because we couldn't assume that the bribery you're involved in or they're involved in necessarily applied to your business. And it's the same thing that's going on with answer number 1 here. And answer number 1 doesn't even tell us explicitly that the consultant has taken bribes, merely that the consultant is being investigated for bribery. So it's not quite specific enough. And so we're going to rule out answer number 1. So let's have a think about answer number 2. Answer number 2 is in fact the correct answer. And so why? It's important to know why. So if we think about answer number 2, it says the mayor was aware that many of the bills were being presented to the consultant rather than to the mayor. Now, if the mayor knew that all of the bills were being sent to the consultant and just knowingly let it happen, but then, you know, the mayor's gone and responded to these critics by saying, you know, who, me? I didn't even get any bills. So his whole argument starts to look very shady. And so that's why this is the correct answer here. But, you know, okay, the mayor can say, I paid for everything that was presented to me, but if he knew that hardly anything was being presented to him, that doesn't really tell us much. So let's think about why 3 and 4 are wrong, given that 2 is the correct answer here. Well, 3, okay, we're pretty much already told this. 3 says the building contractor in charge of improvements to the house had done business with the city in the past. That's what we're told in the premises. This doesn't really address the mayor's response in any way. And that's really what we're trying to weaken, is the defense from the mayor here. So 3 is wrong for that reason. So why is 4 wrong? Well, 4 really, there's a sense in which the information in it is irrelevant, because it just doesn't matter how much the consultant was being paid here. They could have paid the consultant more or less exactly the same. And in any case, you know, the improvements could have been done as a bribe or not a bribe. We wouldn't be able to kind of tell any relevant information from what 4 tells us. And so there's a sense in which it contains something irrelevant. That's why 4 is wrong here. And so, top tips for these types of questions. What to look for in weaken. And, you know, you might see examples of strengthen questions. I'm going to talk a little bit later on about what you should be looking for in those types of questions. What can we say about this question? So tip, the answer here, so this is something worth looking for. It's consistent with the premises. But it undermines the conclusion. That's what we said when we were talking about why number 2 is right here. So that's something to look for. You're looking for an answer that's consistent with what's in the premises, but it leads to kind of a different conclusion, or it undermines the one that's given there. So that's tip 1 when you're looking for an answer that weakens an argument. Another tip, and this is a big one. The answer sometimes in weakened questions provides an alternative explanation for the conclusion that's given in the argument. Not so much here. Our example here really fit the first tip a little bit better, but this is definitely something to look for and worth practicing. So this is in weaken questions. And what else did we say? So my third tip for these types of questions is beware of irrelevant information. That should help you rule some of the answers out, and it will give you a better chance if you are guessing it correctly. So what do I mean by this? Look carefully at what's in the conclusion. The answer should talk about things that are specifically talked about in the conclusion. in some types of these questions. So whenever you see irrelevant information or tangential things that are being talked about in the answers, it should raise a red flag for you. You should be eliminating those types of answers. This third tip goes for strengthened questions as well, which I said we'll come on to a little bit later. Okay. So we've looked at validity, we've looked at inductive probability. These are two types of questions that you can expect to see again. So it's worth having a good practice by looking back at what we've already done, use assignments 1 and 2 to get that practice in. Any questions? We should pause, see if anyone's got anything. Oh, Tom, I've just seen your chat. You were correct. Okay, no questions, let's move on. So here we are on the left again, looking at the roadmap. So we went to weeks 1 and 2, we took the chapter test, and then we hit weeks 3 and 4, where we started looking at some philosophical problems associated with inductive logic. And then we stopped at the end of week 4 after we'd seen these problems, and that's what this mountain is supposed to be. So let's have a recap of these topics that we covered in weeks 3 and 4. We hit Hume's problem of induction. And that's what this mountain on the last page was supposed to be. It's a big, big old problem. And, you know, it doesn't really have a solution even today. So we met this problem. We looked at some potential ways around it, but we also looked at why those potential solutions to Hume's problem were in fact wrong, so they fall short in some way. One of them was this one, the inductive justification of induction. The other one was the pragmatic justification of induction. And then we moved into week 4. We started looking at projections and regularities. And how we finished in week 4 was looking at Goodman's paradox, which is kind of a newer problem of induction. Now, focus for the final will be on Hume's problem of induction. Why? Because it was the least well done thing on your second chapter test. People dealt very well with Goodman's paradox. What this usually means is I taught Hume's problem of induction poorly. So we're gonna have another crack at it. So what I've got over here is one of the old large group problems, which really goes back to basics with Hume's problem of induction. It asks you to diagram it, essentially. So what you've got to do, you've got to fill in A, B, C, D, E, F, G, H in these boxes, which is kind of a pictorial representation of how Hume's argument works. So what I'm going to ask you to do, I think will take 5 minutes or so. I'm going to ask you to have another go at this. Now, of course, we've done this before, but you know that's the purpose of revision and finals, is to test you again on stuff you've done before. So do try and have a go without looking at notes or answers, things like that. Really test your understanding of this argument. So fill in the letters in the boxes. And then what I didn't ask you when I've asked you this question before is another question down at the bottom here. Says, how do you explain the arrows that are colored red? So have a think about how you would explain the implication that's represented by those red arrows. And after that 5 minutes is up, we'll come back together and I will carry on talking. Okay, so we'll come back together and very quickly we'll fill in this diagram. So at the very top, so what is Hume arguing for? Hume's argument, the conclusion of it is that we can't rationally justify a system of induction. So perhaps the easiest thing to put in is very down at the bottom here. Hume's main conclusion is C. We can't rationally justify a system of induction. Now, what did we say about how he argues for this? What's the structure of this argument? Well, it's an argument by contradiction. And so the very next step up from the bottom, we're going to have H, which was contradiction. And how do we know, or what do we know about how arguments by contradiction work? Well, whatever the main conclusion is, we'll start up at the very top by assuming the opposite of that main conclusion. So D should go at the top here. D says we can rationally justify a system of induction. So how do we proceed? It goes, we can rationally justify a system of induction. We're going to do some reasoning. We're going to derive a contradiction. And it follows that we can't, after all, rationally justify a system of induction. That is the structure of Hume's argument. So we've got to fill in these other five. What goes under D? Well, that just comes down to what Hume thinks it takes to justify a system of induction. So if we can rationally justify a system of induction, then we can do what F says. So this is what Hume thinks it takes to justify a system of induction. So we can show that the arguments to which that a system assigns a high inductive probability give us true conclusions from true premises most of the time. And then the E arguments to which that system assigns higher inductive probability yield true conclusions from true premises more often than the arguments it assigns a lower probability to. So that's what we'd expect, at least according to Hume, from system of induction. So if we can do that, so if we can show what F says we can show, the idea is to think about, well, how would we show that from Hume's perspective? And what Hume says is, well, you can show this in two ways. You can show it using a deductively valid argument. That would establish what we want. Or you can show it using an inductively strong argument. That would also establish what we want, because they, remember, deductively valid and inductively strong, they are the good arguments. So if we're going to show this and we're going to claim we've shown what F says, we'd better have shown it in a convincing way. So you should have G and A in these boxes. So deductively valid, that's G. Inductively strong, that's A. And now we run into the problem or the contradiction. So what happens if we try and show this using a deductively valid argument? Well, and this was done pretty well on this chapter test. It was recognized that the conclusion falls short of the desired goal. That's the kind of slogan that we've put into this argument here. What happens if you try and show what F says you can show using an inductively strong argument? Well, you end up begging the question. That's the last one, that's E. However, what wasn't done so well on the test was explaining why, if you try and use a deductively valid argument, you fall short of the goal, aka explaining this arrow here. Wasn't done so well. And similarly, what wasn't done so well was if you try and show this using an inductively strong argument, why you are begging the question. So it's all well and good to know that you're begging the question, but why? We're interested in why. So that's why I've asked you down here, how do you explain these arrows that are colored red? And so I'm going to walk you through what I expect from an explanation of these arrows here. So let's look at this one first, the deductive one. So why, if we try and use a deductively valid argument, are we falling short of the goal, or does the conclusion fall short of the goal? So first thing to note, this is what we said in the videos about this. The premises in this deductively valid argument can only refer to the past or the present. Because that deductively valid argument would take the form of something like all these arguments I've used in the past, where scientific inductive logic has assigned a high inductive probability to, all the ones we've used in the past have given us true conclusions from true premises most of the time. That's how this argument would have to start. So the premises can only refer to the past and the present. But what do we know? It's annoying. Conclusion of this argument can also only refer to the past and the present. Why is that? Well, the conclusion of a deductive argument or a deductively valid argument can only refer to what the premises have already referred to, even implicitly. So the conclusion of deductively valid arguments cannot go beyond what's already in the premises. So if we're using a deductively valid argument to establish what we want here, and the premises refer to the past and the present, then the conclusion can only refer to the past and the present. And that is why the conclusion falls short of the desired goal, but we need the conclusion to refer to the future, not just the past and the present. Because we want to be able to say all arguments, past, present, and future, that scientific inductive logic assigns a high inductive probability to, give us true premises from true conclusions from true premises most of the time. That's what we need from the conclusion. So that's why it falls short of the goal. On the other side, why, if we use an inductively strong argument, are we begging the question? That goes like this. So the explanation of this one, you would say, okay, here's an inductively strong argument that shows what F says we can show. And you would ask, if this argument is inductively strong, what makes it that way? What makes it so? And you would want to reply something like, scientific inductive logic says it's inductively strong, of course. And what's happened? Well, you've used the reliability of scientific inductive logic to justify the reliability of scientific inductive logic. This is the very thing, remember, that we're trying to justify. So, but that is the very thing we're trying to justify here. And so you've begged the question. That's what begging the question means. It's a type of circular reasoning. So you've assumed what you want to get what you want. And that's bad news for the argument. So that explains the red arrow here. That's why this is begging the question. You end up appealing to what you want to show. And these explanations of these two arrows is important. I really want people to be focused on this. I really want us to nail this down on Monday. So any questions before we move on about Hume's problem?
I do have a question. Is this kind of the general setup for all of the questions, or are they going to vary in some kind of way?
This one won't be in the form of like a pictorial representation like I've given here. If you're asked about Hume's problem or certain aspects of it, that will vary a little bit. The weaken, strengthen type questions that you've seen before and that we did before, you can expect them to look the same. That's just the form of those questions. Same with test this argument for validity. It'll just be argument test if I ask you to do that.
Okay. Like, do they not help? I'm just wondering though, do they normally start out with like um the top one being the uh starting out with trying to rationally justify something um as an induction, and then you're gonna end it with like that you can't?
I see. Yes. If you were, asked maybe to describe Hume's argument, something like that. I think I've asked you to do that before. You would write down what this picture says. So you would start with D. You would say, suppose we can rationally justify a system of induction. Or you would say, look, this is how his argument goes. You start by assuming he can do this. Reason, 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 reason. Therefore, we can't do it after all. Does that make sense, Emily?
Yes. Yeah, thank you.
Okay. Yeah, so this is a complete kind of picture of what Hume argued, how his argument goes. Okay, so that's weeks 3 and 4, the highlights and the focus. Let's move on. So back on the roadmap, over on the left, we did weeks 1 and 2, we stopped for some highlights, some pictures. We did weeks 3 and 4, we stopped, we looked up at Hume's mountain here, said, wow, that's a problem. We can't really climb it either, can't see how to get around that. We saw how all of the solutions that have been proposed, the inductive justification, the pragmatic justification, they failed. So instead of trying to climb Hume's mountain, we went around it in a sense. So we moved into weeks 5 and 6, and we tried to do something a little more constructive. We stopped and we said, okay, we've seen some problems. Well, can we make any kind of progress, even if we can't solve them completely? And so that's what weeks 5 and 6 started to look at. We started to look in particular at the scientific method. And what that amounted to was looking at kind of cause and effect and how we can start to talk about this idea of cause and effect. So now we're here, weeks 5 and 6. We've stopped for some highlights. What did we see in weeks 5 and 6? We saw the following things. We were introduced to necessary and sufficient conditions that gave us a way to talk about when one thing, X, might cause another thing, Y. Perhaps X is necessary for Y, perhaps X is sufficient for Y. Then we did a lot of Mills methods involving tables and eliminating things as being sufficient, eliminating things as being necessary for certain properties. Then we started to look at how we might mathematize this, and that was functional relationships. We started talking in terms of equations and how they express sufficient conditions. And then we finished by talking about accidental and law-like conditions. So what we're focused on for the final is those things in blue, necessary and sufficient conditions and functional relationships. Now, I said back in weeks 5 and 6 that necessary and sufficient conditions, really, of course, the whole 2 weeks were about that. That was the focus of those 2 weeks. But there were different ways that I would test your knowledge of necessary and sufficient conditions. There were A, filling in those tables and using Mills methods, and B, looking at written English arguments and being able to pick which conditions are sufficient for a conclusion, which conditions are necessary for a conclusion. I have chosen to focus on the second type of those questions. So this is what you should be practicing for the final. So let's have a look at an example question. The sort you can expect to see testing your knowledge in this area. So again, it's one of these written English arguments. You've got 4 principles and you've got to pick the one in this case, which is sufficient. So it says, consider the argument below. Which of the following principles is sufficient to justify this argument's conclusion? And again, it says you do not need And to justify your answer, that means do not leave this blank. Please have a guess. So the argument says, premise one, almost all books that offer management advice are written from the perspective of the CEO. Premise two, most managers aren't CEOs, don't have the same perspective as CEOs. Therefore, conclusion, the advice in management books is of limited use for most managers. So what we're going to do, you're going to take 2 or 3 minutes, have a look through 1 and 4, keep the answers to yourself just for now, just try not to influence others' thinking patterns too much. And then we'll come back together after 2 or 3 minutes, and we'll talk through which one is right, and also importantly, why the ones that are wrong are wrong. So I'll read them out very quickly. 1 says advice books rarely take the perspective of their intended audience. 2 says most people who read management advice books aspire to be CEOs. 3 says advice is of limited use unless it is offered from the perspective of the recipient. It's a typo. And 4 says most managers prefer to read books that they think they will be useful to them in their work. So take a couple of minutes, have a think, which is sufficient? And I'll go through which one is correct. And again, I'll offer some tips on how to approach this type of question. Okay, so let's have a think about this question. So let's look at number 1. And we're asked which is sufficient. So sufficiency, we're thinking immediately, okay, there is some sort of gap between the premises and the conclusion, and my answer has to fill that gap. So which one of these implies this conclusion, or is enough for this conclusion to be true? Number 1 says advice books rarely take the perspective of their intended audience. But number 1 isn't quite what we want. Why is that? Well, how often this in number 1 does or does not happen kind of wouldn't help us make the conclusion. It still leaves open this gap that we're looking to fill of, can you get a lot out of a book written from the perspective of someone different from you? That's the gap we're looking to fill. That's the issue here in the argument. 1 doesn't fill it. So we're going to rule out 1. Number 2 says most people who read management advice books aspire to be CEOs. Now, let's have a think about what we're trying to say here. What we're trying to say is that most managers do not get much out of these books. That's what the conclusion's getting at here. If most people reading the books are trying to become CEOs, it seems like they might actually get a lot out of these books. So this, what number 2 says, is going to be in the opposite direction of what we want. So this is not going to be sufficient for the conclusion. I'm going to rule out number 2. Number 3. Number 3 is the answer to this question. What number 3 says is that if advice is not offered from the perspective of the recipient, then it's only of limited use. So although number 3 goes a little bit broader than just managers and CEOs, that's okay. All we're looking for is enough for the conclusion, and this gives us more than enough for the conclusion to work. So if it's true that advice written from a different perspective than its recipient will only be of limited use for that recipient, so the person who's going to use it, then it would have to be true that advice written from the perspective of a CEO will only be of limited use to most managers, since most managers are not CEOs. So number 3 is what we want here. Tick. That leaves us to justify why 4 is wrong. Well, what does 4 say? It says most managers prefer to read books that they think will be useful to them in their work. But whether or not they prefer to read a certain kind of book isn't going to tell us anything about the quality of advice given in that book. So there's a little bit of irrelevancy to number 4. That's why number 4 is wrong. So pause, I'll check the chat. So what have we said? Let's write down some tips for approaching this type of question. Sufficiency questions, like we said before we went through the answers, identify the gap between premises and conclusion. The answer will bridge that gap. So you're looking to fill in a gap when it's sufficiency that you're looking for. Again, just like before, beware of irrelevant information. If you are looking to fill a gap between the premises and the conclusion, and you see an answer choice that talks about something that isn't in the premises and isn't in the conclusion, it's probably not going to bridge the gap for you. So if there's irrelevant stuff in there that should raise a red flag, you should be eliminating it. And that will make this easier for you if you don't know immediately which one is right. Another tip. This is testing necessary and sufficient conditions. So one way to think about how to approach these questions is the following. Sufficiency, what does that mean? We've seen the definition of sufficient condition a million times. So think, if blank is true, then the conclusion has to be true. That's what it means for an answer choice to be sufficient to justify this argument's conclusion. And your job, of course, is to fill in this blank with the correct answer choice. I know we haven't been through one here, but you could also just as well be asked about necessariness. So the corresponding way to think, if you're asked which of these following principles is necessary for this argument's conclusion, we know what it means to be a necessary condition for the conclusion. It means if the conclusion is true, then blank has to be true. And of course, your job is to fill in that blank with the correct answer choice. So if you're asked about necessary conditions, it's asking what's assumed by the conclusion? What has to be true if this conclusion is true? Now, I said back at the beginning I would return to strengthen questions. That's because my top tips that we've been through here for sufficiency, so for questions like this, they are kind of the same tips I would give you if you're asked which of these following principles strengthens this argument or justifies this or supports this argument's conclusion. Look for that gap between the premises and the conclusion. You are almost looking for a sufficient condition for that conclusion if you are asked which one of these principles strengthens an argument. So that's what I wanted to say about strengthen questions. Use the same kind of tips that we've given here for sufficiency questions. Okay, looking back over at the left, that's what I expect you to be able to do and deal with necessary and sufficient conditions, really applying this material to think critically about arguments here. Moving on then, functional relationships. What I want to say about functional relationships, you have seen this question before. I believe it was on a chapter test. It wasn't done so well. However, I think this is just a kind of, so again, returning to the things that make questions hard. Either you couldn't do it on a test or it's conceptually difficult. This, I do not think, is conceptually difficult. This is more like a banana skin where most people slipped up in the chapter test. So I'm going to go through how you do parts 1 and 2 with this type of question. Okay, so it says it's about Coulomb's law. So law of physics quantifies the amount of force between two charged particles. Relates the force F between two particles to their charges, Q1 and Q2, and the distance r between them. So suppose we're interested, as usual, in which of two functions correctly expresses Coulomb's law. So here's function 1. It's f equals k times Q1 times Q2 divided by r. And function 2 is k times Q1 times Q2 divided by r squared. And here k is a constant and r is non-zero. So you were asked a couple of things first. People did well on these other parts. And this was the end of this question. It said, suppose you measure the force between two particles with these charges. So Q1 is 3, Q2 is 2, and r, the distance, is 2, using k, your constant, equals 2. And I'm asking which of the following values of f eliminates only function 1. This whole thing is key. Eliminates only function 1 as given the correct sufficient conditions. And similarly, which of the values of f eliminates only function 2. So the way you do this, first you identify the sufficient conditions, and I do want to say something about this. So identify sufficient conditions. Another type of thing I asked in these questions is, did you which of these sufficient conditions allows you to distinguish between these functions? And what emerged from people's answers, or at least I think so, to those questions, is what are the sufficient conditions here? The sufficient conditions is not just R, or it's not just Q1, or it's not R and K, or it's not R and Q1 and Q2. The sufficient conditions are all of these values. Think of them as all together in a little collection. So we've got K, R, Q1, and Q2. This is the sufficient condition. It's all of these values. So whereas people were writing things like, oh, when it's sufficient condition R, you can tell them apart. Or when it's sufficient condition K equals 2, you can tell them apart. The sufficient condition is all of the values. So you would have to specify a value for each of these letters. That is one sufficient condition altogether for F. Because of course, R on its own won't determine F. You need to know all of the values to give you a value for F. That's why all of them constitute the sufficient condition. So it's not just one or two. That is important. Okay. So the question is, let's try and leave the functions on there. We are given the numbers. So Q1 equals 3, Q2 equals 2, R equals 2, K equals 2. So we substitute them into function 1. Let's do that first. We get F equals K, that's 2, times Q1, that's 3, times Q2, that's 2, all divided by 2, which is all divided by R, which is 2. If we calculate that, it's 6. Similarly, if we throw them into function 2, what do we get? We get F is K, that's 2, times Q1, that's 3, times Q2, that's 2, divided by R squared. R squared is 4, because R is 2 here. So if you calculate that, you're going to get 3. It's half of function 1. Now, what the question is not asking you is, what does function 1 give you? And that is how a lot of people answered this question. They said, okay, function 1 gives me 6, so the answer to part 1 is 6. Not true. I'm asking you which of the following values of F would eliminate only function 1 as giving the correct sufficient conditions. So first thing, let's focus on eliminate function 1. So ignore the only part first. Well, if I'm going to eliminate function one has to be wrong. Since function 1 tells me the answer should be 6, it has to be one of the other numbers, not 6. So if I'm eliminating function 1, 3, 4, or 5 will do the job for me. But I don't want to eliminate function 1. I want to eliminate only function 1. That means I want to leave function 2. So function 2 has to be left. Which of those numbers, 3, 4, and 5, leaves function 2 as possibly correct? Only one of them, 3, because that's what function 2 gives me according to these numbers. So the answer to this one should be 3. So it is not 3 numbers like some people put. It's not 6 because that would make function 1 correct. It wouldn't eliminate it. It's the one that makes function 2 correct. And similarly, if we're going to eliminate only function 2, by exactly the same line of reasoning, you would have to pick 6. Function 2 tells me the answer should be 3. So 4, 5, and 6 will eliminate function 2. But if I'm going to eliminate only function 2 out of these two functions, it's got to be 6 because that's the only one that will leave you function 1 as being possibly correct. So, you know, where you've got to plug these values in and see what the functions give you, but that is not what the question is asking. But it's opposite to what the question is asking in a way. So that's how you go about these eliminate only questions. Be one number, not 3. Okay, we're going to move on. We're probably running short on time. So that was weeks 5 and 6. That's what you can expect on Monday, things like that. So looking over at the left again. Now, what we did at the end of 5 and 6 was we moved into looking at probability, and that's why we've got this other mountain here, because there's been a lot of math for the last 4 weeks or so. And, you know, I'm sure it's been a bit of a slog for some people. So we started climbing this mountain. We started developing the probability calculus. We looked at expected values, things like that. And then we stopped in week 8 for some pictures. What did we see? Weeks 7 and 8. Like I've just said, we spent a couple of lectures developing the calculus itself. We hit expected values, which kind of recurred in various forms towards from then till the end of the course. We looked at Bayes' theorem, clearly a huge part of this course. That's recurred again and again and again from when we met it till when we finished. And we also met this other form of Bayes' theorem, the odds form of Bayes' theorem. Now, focus for the final, Bayes' theorem and the odds form of Bayes' theorem. What I am not going to do is go through an application of Bayes' theorem. The reason is that it was very, very well done on the chapter test, at least the part of, or the level of question that involves Bayes' theorem that you can expect to see on the final was very well done. Keep going with that. The videos, what's in that video, whichever one Bayes' theorem was, I think it was 22. What you meet in that video will be adequate preparation for what you can expect on Monday. Won't be anything as hard as the Bayesian search theory question where I was asking you to find a submarine. But what wasn't done so well was the odds form of Bayes' theorem. So here it is. This is what I asked you a couple of weeks ago, with the exception of part C, which I'm not going to go through. What I am going to go through is parts A and B of this question. And I want to describe the procedure of how people should be going about this form of question. So what's the question say? It says, you might think Bayes' theorem would be useful in a legal setting where evidence is presented all the time. Suppose you're on a jury listening to a trial and the prosecution presents some evidence. The evidence is a blood sample of the criminal found at the scene of the crime, matches the blood type of the defendant. And we suppose that the blood type, regardless of whether they're innocent or guilty, the blood type is found in 1 in every 10 people. A says, calculate the Bayes factor and interpret it. And it gives you a little assumption in there. So you assume that the probability that the blood sample matches the defendant, given that they are guilty, is 1. B says, calculate and interpret the posterior odds in favor of the guilty hypothesis in light of the evidence. And you've also got some information about your prior probability that the defendant is guilty in part B. Now, what I want to do before I give you a couple of minutes to think about how to go about this is I want to tell you how you should start these questions. The first thing you do is label things in an appropriate way. So we're talking about hypotheses and evidence, and of course the odds form of Bayes' theorem has a lot of probabilities involved in it. We've got to label things appropriately. That will help us set up the answer to this question. Now, the odds form of Bayes' theorem, of course, says this: P of P given Q over P of not P given Q, P of Q given P over P of Q given not P, times P of P over P of not P. And what we're talking about here is hypotheses and evidence. Q here is the evidence. P is one of your hypotheses, not P is your other hypothesis. So what we're going to do is label things appropriately so we can start working with this theorem. So we're going to let P be the hypothesis that the defendant is guilty. And therefore not P is the hypothesis that the defendant is innocent. And we're going to let Q be the evidence, blood match with defendant. That was the evidence presented by the prosecution, so blood match. So if we start, not Q, will be no blood match here. So we start thinking about what we need here. And remember, in the videos, I went through a table of how you do this and organize this information. Oops. Okay, the table looks like this. We had our hypotheses. We had the likelihoods, and we had the priors. And these things are all involved in calculating and using the odds form of Bayes' theorem. Now, the hypotheses in this case are guilty or not guilty, innocent. And so what the likelihoods are asking for, and this is where a lot of people kind of went wrong with this question. I'm just going to unplug this and put it back in because it's lagging a lot. We're back. Just resize things so you can't see all my folders. all of the videos that I've been making for the last 10 weeks. Okay. So what are the likelihoods here? The likelihoods are the things you need to calculate the Bayes factor. So the likelihoods in this example are, oh good, the lag is gone. P of Q, so blood match, given P, so given guilty. P of Q, so blood match, given not guilty. So they are what the likelihoods are in this example. What are the priors? The priors are just your probability on guilt and innocence. So your probability on P and on not P. So take 1 minute and have a think from the information in the question. What are the likelihoods and what are the priors here? So A, you'll only need the likelihoods for. B, you'll only need you'll need everything for. Okay, hopefully we've had a think about what these values are here. First likelihood, probability of Q given P, or the probability of a blood match given that they are guilty. You are told in part A that the probability that the blood sample matches the defendant given that they are guilty is 1. So this likelihood is 1. Next likelihood, probability of a blood match given that they're innocent. Well, the probability of a blood match given that they're innocent, and this is where some people kind of got stuck here, it's just the probability of that blood match being found in a person. And you are told that that happens in 1 in every 10 people. That's part of this description in the question. So the probability of a match, given that they're innocent, is just the probability of a match. That's going to be 1 in 10. So this is 0.1. So we can do part A at this point. Calculate the Bayes factor. The Bayes factor is this thing. P of Q given P over P of Q given not P. So Bayes factor is 1 divided by 0.1 is 10. This, we said, was positive evidence from our table about how you interpret these numbers. So that's how you do part A. Part B says, suppose you think the probability that the defendant is guilty is 0.55. That means your prior on P, because P stands for guilty, is 0.55. That means your prior on not P is 0.45. It's 1 minus your prior on P. That's how negations work. And so we can plug everything in and calculate the posterior odds. So B, posterior odds, equals the Bayes factor, 10, we've just calculated it, times the prior odds, I'm looking up here, P of P over P of not P, 0.55 over 0.45. I think, plug this in to a calculator. Yeah, this comes out to around 12. That's all you need to do to calculate the posterior odds. When I ask you to interpret the posterior odds, I am asking for something like this. Because this is bigger than 1, this number, you know it's in favor of the hypothesis that's on the top here. So it's in favor of P, sorry, it's in favor of P. P was the guilty hypothesis. So you would say it's around 12 times more likely that the defendant is guilty. That's the hypothesis this is in favor of, rather than innocent given the evidence. That's how you interpret this number. So you would say something like that. That gets you the points for the interpret part of this question. Okay, you can also say, I would also accept something like the odds after you've seen the evidence are around 12 to 1 in favor of the guilty hypothesis. So you can interpret this in terms of odds, or you can interpret this in terms of probability. Either one is fine. And so that's how you do these questions. Now, one thing that did occur to me was that maybe it was my wording of the question that made this difficult. So I will try and fix that for the final. You can certainly expect to see the odds form of Bayes' theorem. Again, though, like I said here, make it simple for yourselves. Label things appropriately, write out the theorem, figure out what you need to match up with the letters. Do this table, organize it, and then these numbers should be easier to keep track of and work with. Okay. Any questions before we hit weeks 9 and 10? I'm trying to keep up with the chat.
I have a question.
Wei Min, go for it.
Yeah. You mentioned that the probability of not guilty is equal to the probability that's found in the blood. I'm not sure. Yeah, but why is that?
So this probability was the thing that's 0.1. So this is the probability of a match given that they're innocent. We're thinking of the probability of a match and the defendants being innocent. They are independent statements here. Let me write this down. So blood match, that's right, blood match and innocent are independent. So learning that, you know, he was innocent of this crime, it doesn't tell you anything about whether the blood will match or not. And what do we know about independent statements? Let me make sure my P's and Q's are right. So P of Q given P is just P of Q. That's what it means for these statements to be independent. And remember, this is blood match. This is innocent. Sorry, this should be a not P. That's innocent. This is blood match. So the probability of a blood match, given that they're innocent, is just the probability of a blood match. And so that's 0.1. That's just what the question tells you.
Yeah, got it. Thank you.
Okay. Yeah, that's a good question, though. That's where a lot of this started to go wrong for people. But like I said, I have tried to clean up my wording of the question, so hopefully makes it a bit more straightforward for people. Okay, we're going to move on to weeks 9 and 10.
Excuse me?
Yeah.
Sorry, I have trouble labeling things. I always mess up like P and Q, like which one is P, which one is Q.
Yeah.
So yeah, could you please maybe give more tricks to label? Thank you.
Yeah, I would start. So this is just for this type of question. If you're working with the odds form of Bayes' theorem, write this out first. So write out the theorem. Now, it doesn't matter which way round your P's and Q's go in this theorem. What matters is your labeling to match up with what you've got in the theorem. So start by writing this out. And if you've written it out like I have here, so P is the hypothesis, Q is the evidence, then that's what you need to match up with. I don't think that will be problematic. when you meet the odds form of Bayes' theorem on the final. I think if you write out this theorem first, so that's my top tip, you'll be okay with this. I've tried to be more transparent about what the hypotheses and what the evidence are. Yes, you can screenshot whatever you like. Okay, let's move on. We're almost out of time to weeks 9 and 10. So on the left, we have finally climbed probability hill, or whatever you want to call it. And we reached the end of the course, which is today. So congratulations, everyone. And later on, some of you are going to stop and take some pictures in the form of a chapter test. So what have we seen over weeks 9 and 10? We've seen rational degrees of belief in some detail, and that was all our work on expected utility theory. We've seen relative frequencies and chance, and we've seen that these are 3 different ways that one might use the word probability. You might have 3 different things in mind, and they're all slightly different. Then week 10, we saw hypotheses and deduction, and we saw evidence, a bunch of different kinds of evidence and why that evidence is important. Finally, convergence to the truth, where we brought back the discussion to Hume's problem, in a sense, and we asked, well, what can we say about Hume's problem in light of what we've done? For the final, expected utility theory will be important. So will your work on evidence from this week and convergence to the truth. We are going to conclude by going through a question about expected utility theory, in particular, figuring out your degrees of belief given a certain scenario. So we scroll down to the last question. Now, given that this chapter test hasn't happened yet, I'm not sure whether this will be done well or not so well from those people who take it. So this is on there because I think it's really a culmination of what the book is really getting at when we're talking about recovering degrees of belief. So these types of questions show you exactly how you figure out your degrees of belief from preferences about certain things. So I want you to have a think for 4 or 5 minutes about how you would go about this question. And then what we're going to do, we'll come back together and I'll walk through the solution. And then hopefully with about 5 minutes left, we'll pause for some questions. Again, this is something to focus on for the final, this type of question. Okay, so what we're going to do is walk through how you do this type of question. Now, there are 3 parts, and that's typical of this type of question. First 2 are very easy, and the third one is more involved. So, you know, as usual in this type of question, 2 people are going head to head in some kind of sports match. And to be honest, I'm running out of sports at this point. So this time it's Ben and Nathan, and they're fencing. And I offer you the following bets. And the bets are always in the form of 2 acts. So that means we're reasoning under uncertainty here. These are states of the world acts. That's all mathematics of uncertainty. Act F is a $5 bet at 4-to-1 odds that Nathan will win. And G is a $5 bet at 7-to-2 that Ben will win. Now, I don't want people worrying too much about the odds here, because what's important are the payoffs, which I will always give you in a table like this one. So payoff according to Act F, that means, let's write, I'm looking here in this cell. That means if you make Act F, so if you take the bet in Act F and Nathan wins, you'll win $20. That's what that cell means. On the other hand, if you take Act F, but Ben wins, so the other outcome, you'll lose your stake. You'll lose what the bet cost you, so you'll lose $5. Act G, if you make the bet in Act G, Act G is a bet on Ben winning, but Nathan wins. That corresponds to this cell in the table. You're going to lose your stake, $5. And if you make the bet in Act G, so finally this fourth cell, so you bet on Ben, and in fact Ben wins, then you'll win 1750. That's what the odds mean. So they are the payoffs. And it says, suppose you take exactly one of my bets so that exactly one of the payoffs occur. And you want to scale all your utilities so they're on this 0 to 1 scale. Now, the first two questions in this type of example will always ask you which one's 0 and which one's 1. That's why they're very easy. So 0 corresponds to the worst thing that can happen to you in this situation. The worst thing that can happen is losing $5. So U of -5 is your 0. Similarly, what's 1? That means it's the best thing that can happen to you. Well, the best payoff, according to this table, is you winning $20. So U of 20 is your 1. That's the best thing that can happen to you. Part 3 is then more involved. And I'm going to speed through this. So it says, suppose you are indifferent between F and G and you're maximizing expected utility. And then I give you the rest of your utility scale. So I say, suppose you'd be pretty happy with winning $17.50. So U of 1750 is 0.9. And then I ask you the question itself, what's your degree of belief? So that's what we're recovering, remember, in Nathan winning. And what's your degree of belief in Ben winning? The steps doing this question. First, write down expected utilities according to each act. What that means is expected utility according to F. That is your degree of belief in outcome 1, so in Nathan winning, times how happy you'd be if you took bet F and Nathan won. That corresponds to you winning $20, so times U of 20. Plus your degree of belief in Nathan losing. That's the same thing as your degree of belief in Ben winning. Times your utility of the outcome that corresponds to you taking Act F. So you've bet on Nathan, but Ben wins. And in that case, you lose $5. Similarly, the expected utility according to G. Again, it's your degree of belief in Nathan winning, but this time, if you've taken bet G, you've bet on Ben winning. So what would happen if Nathan won? You'd lose $5. Plus your degree of belief in the other person winning, Ben, times U of what? Well, what happens if you take Act G? So if you bet on Ben and Ben wins, that's the very last payoff in the table. So that's 1750. So they are the expected utilities according to these acts. The second thing you do, substitute in your utility scale numbers. We know from parts 1 and 2 that U of -5 is 0 and U of 20 is 1. I then tell you that U of 1750 is 0.9. So expected utility of F becomes, we're going to rewrite this thing here, degree of belief in Nathan times 1, that's U of 20, plus degree of belief in Ben times 0, that's U of -5. And this simplifies to just your degree of belief in Nathan winning. You do the same thing for Act G, sorry. Expected utility of G. So this time we're going to rewrite this. It's your degree of belief in Nathan winning times U of -5, that's 0, plus your degree of belief in Ben winning times U of 1750. I told you that's 0.9. So this simplifies to 0.9 times your degree of belief in Ben winning. Third thing you do is use the right representation theorem. That allows you to solve these questions. The focus, of course, in those videos was applying these theorems. What this means is you take the bit of the question that tells you about your preference between F and G, so whether you prefer one to the other or whether you prefer them equally, and you translate that into a statement about your expected utilities according to those acts. That is how you apply these theorems. Now, we met two in the videos. The first one was when we were reasoning under risk. That's the first representation theorem. The second one works when you are reasoning under uncertainty. That was the second representation theorem. Here we are reasoning under uncertainty, so we are going to use the second representation theorem. And you would say something like, by the second representation theorem, what does it say about my preferences between F and G? Up at the top there, it says, suppose you're indifferent between them. You prefer them exactly the same. So you prefer F and G equally. What does that mean? By the theorem, your expected utility according to F, that's your degree of belief in Nathan winning, that's here, equals, because your preferences are equal, your degree of belief, your expected utility according to Act G, that's here. We're almost there. Last thing you do is solve this equation for your degrees of belief. We know that my degree of belief in Ben winning is 1 minus my degree of belief in Nathan winning, because there's only two of them in the match. I believe exactly one of them will win. So we substitute that into this. Let's call it star. So star reads, degree of belief in Nathan is 0.9 times 1 minus my degree of belief in Nathan. And then we solve this. So we expand those brackets. This becomes degree of belief in Nathan is 0.9 minus 0.9 times degree of belief in Nathan. Take this term over here. So I'm going to add 0.9 to 1. So 1.9 times degree of belief in Nathan is 0.9. Finally, we divide by 1.9 to get my degree of belief in Nathan winning this match. We do that in a calculator, it's about 0.47. So you've got your degree of belief in Nathan winning the match from your preferences about these bets. And so your degree of belief in Ben winning is 1 minus your degree of belief in Nathan winning would be 0.53. So that's how you do this question. You write down your expected utilities first. Circle things. Second, you simplify them by substituting in your numbers for your utilities. And I'll always give you those as long as you can figure out which is 0 and 1 yourself. Third, use the representation theorems. That's, you know, the upshot of a lot of work that we've done on expected utility theory, being able to apply those theorems. And last, you solve to obtain your degrees of belief. Just before we stop for questions, let me run through the end of these slides on the left. So here we are. We've finally got to the top of this probability mountain, and there we are. We're looking over where we've been, where we've come from. And, you know, Hume's problem, this is the whole point of the work on probability theory. There it is in the background. It doesn't look so daunting anymore, right? We've, okay, it's unanswerable in its purest form. That's what we said in week 10. But a lot of work on probability theory has shown us that we can give an answer that's pretty much the best answer you can give to Hume's problem. And, you know, for many people, that pretty much counts as a solution to Hume's problem. I can believe that my degrees of belief will converge to the true chances. So there's not really any room for that much skepticism anymore. So we've got a nice view there. Emily, scroll back down. Okay, so that brings us to the end of the review session. These questions I've been through here, they will be useful for the final. Similar questions you'll have seen on assignments. Go back and practice them, like the strengthen, weaken, necessary, sufficient questions. That will be useful. If you have missed some assignments, have a look at them anyway. I know you know the rule is you drop your lowest 3 out of your 9 assignments. So it's not the case that you'll have had to turn in all of the assignments, but there might be questions on those assignments that will serve as good practice, similar to the types of question we've been through here. So any questions before we finish off? Let me stop sharing.
Can we still turn in assignments if they're late?
You'll have to ask me.
Okay.
Came in, you have a hand.
Oh, it was for a previous question.
Oh.
Okay, sorry.
No worries. Tom, the grade automatically drops 3 lowest assignments. Yeah, it's your average of your best 6 out of 9 is the general rule on the assignments. And it's your average of your best 4 out of 5 tests. So you drop your lowest test. Thanks, Patricia. Oh, good. I'm glad. Thank you all for your hard work as well and your input over this quarter. I'm going to stop recording now, I think.